So thank you very much. First, I would like to thank organizers for bringing the conference through in spite of all these Corona times. It's really great to have opportunity to talk about research and not only about Corona. But at the same time, I would say as a speaker, it's a little bit challenging because even if I make jokes and if I would say something no one can follow, I think there's very limited feedback. So that's why I would prefer if there's some questions, so you raise your hands and write in the chat, so that we can have also break during the talk and ask questions. So main topic of my talk today is second order topological superconductivity. In particular, I would talk about Majoranas, but also about parafermions, which are more exotic phases caused by strong electron-electron interaction. But in the beginning of my talk, I also give a small overview about topological systems and current state. So first, what we are hunting for, let's say topological quantum computing also attracted a lot of interest, but as for any computing, topological or not, we need to define qubits, and it's usually done by defining some system of finite degeneracy. Let's say in case of spin qubits, we can define the bound state by just applying gates. And when we apply the gate, then we can have electron confined in a quantum dot, and can manipulate this electron and use it for quantum information. Alternative way to confine state and create a bound state is not applying electrostatic gate, which is tuning potential and using a band gap of material, but we can also use such gaps as superconducting gaps, right? And then it means that if you consider so-called SNS junction, so you have a superconductor, you have normal section, again a superconductor, under conditions that, let's say, that normal section is long enough, we can confine the bound state. In this case, this bound state would also have some superconducting properties, usually referred as Andreev bound state. So here, everywhere we use the gap, and what is important that we have some region, normal region, in which the gap is not there, and then you have just confinement from outside. But when we come to the topological systems, then we have some conditions which guarantee us that we could have a bound state, even if this normal section or section without gap goes to zero. And here I would like to review a model which is coming already from 70s and from particle physics, first produced by Jackie Raby, which kind of solves outline of my talk. In many cases, we would come back to the idea which one can see already from this model. So what we have here is a simple Hamiltonian. It's in the kinetic part here given by linear term. And we try to open a gap in this Dirac spectrum by introducing a mass term. And of course, what we can do about this mass term, we can assume that it has some special structure. So let's say it's positive for positive x, and it's negative for negative x. And then we look at how the structure looks, let's say at momentum equals 0. So when we can forget about kinetic term, when it's very simple Hamiltonian of Dirac matrix, which we can diagonalize. And what we would find, if our mass is positive, then the lowest ground state corresponds to Ty is equal to -1 and upper Ty equal 1. And of course, if mass is negative, so in the side when x is smaller than 0, then it is opposite. And now we consider so-called what we call a domain wall. When you have two parts of a system, let's say positive, negative x, in which gap changes the sign, right? So we go that here upper part was red, Ty is equal to -1, and afterwards it changes and becomes down. So the gap changes sign at x equals 0. And what is interesting in this problem that there's at this domain wall, there's zero energy bound state. And what is nice about it, that is always zero energy bound state, actually doesn't even matter how exactly the mass changes its sign. So here in the beginning, I assume that it's a domain wall. It could have any particular shape, like a non-regular, such that we cannot even solve exactly this differential equation. But still, we can say that we know that there's a bound state, it's always at zero energy. In this case, it's protected. And of course, afterwards, we can use some more fancy mathematical formalism to describe connected to topology and to introduce what protects these states to sit at zero energy. In this case, it would be a particle hole, effective particle hole symmetry. But this is the idea of constructing gaps which changes sign. It also was motivating strongly the field of topological insulators when we try to find materials where a gap is inverted, let's say, due to strong spin-orbit interaction. But this idea was also promising in the field of Majorana fermions, in particular Rashba nanowires. So the setups which I would be referring several times in the talk, and I think you'll hear more about it in later in the talk of Ramon Aguado. But we can see the S-wave superconductor, which needs to induce superconductivity in a Rashba nanowire. So what we mean that there's a Rashba nanowire, it means that we have a spectrum which is parabolic, but two parabolas are shifted away from zero, such that spin degeneracy is lifted at all points except at k equals 0. So now we induce superconductivity and it gaps out because it perfectly couples all Kramers partners to each other. So we induce a pairing from positive momentum to negative momentum, spin up, spin down, and open such a gap in the spectrum. And so here, everywhere, let's say, I work in the regime of strong spin orbits, so I have well-defined Fermi points at k equals 0 and at finite k Fermi. And now, in both points, Fermi points, the gap is opened by superconductivity. And now I'm applying magnetic field. So obviously, I choose a direction which is perpendicular to spin orbit vector. And then it opens a gap at k equals 0. So it opens, usually gap is here. And now if I already had superconductivity, what it happens, it lifts the degeneracy, Kramers degeneracy at this point, and I see the splitting between branches, spin up, spin down at this point. And now if I start to increase magnetic field, at some point the gap is closing at k equals 0, and we have two mechanisms to open gap, magnetic field and superconductivity, but still arrive at the regime at which gap is closed. And if I increase magnetic field further, I find that instead of destroying superconductivity, which is kind of would be common for many superconductors, if magnetic field is strong, the superconductivity properties are disappeared. But in this setup, a strong magnetic field still allows us to reopen the gap. And now we end up with a situation when we have inner gap, which is opened by magnetic field, outer gap is opened by superconductivity. And with some mapping, we can connect back to the quantum, to the model I described before. So there's an interface between magnetic field and superconducting gap, and it acts in the same type as inversion of a band gap. And that's why we can say that this phase is topological, right? And should host Majorana fermions. So where should we find the Majorana fermions? They should be at the, let's say, if nanowire is uniform, so at the end of nanowire should have seen one Majorana fermion, another Majorana fermion at the other end. So Majoranas always occur in pairs, and they should be at zero energy. So that's why when the first experimental test to see if we have Majorana fermions is to check if we introduce some states at zero energy, which should be relatively stable against the direction of magnetic field. And signatures of such states first were seen already in the first experiments in 2012. So the idea that you have state somewhere in the middle of superconducting gap, and it sticks to zero for some range of magnetic field, which naively allows us to distinguish, let's say, from Andreev bound states, which are usually expected to be linear in magnetic field. So recent years, there was a lot of progress of trying to generate these Majorana fermions in experiment, especially in nanowires. There were different setups which were probed. And one of the ideas that we not only need to get into topological phase, right? We also want that there's literally, how I showed, that there's one Majorana on one end of the wire and one Majorana on our end of the wire. And for this, take into account that our wire is not infinite, right? And there's a particular localization length of Majoranas when we try to make this localization length as small as possible so that you can confine it to a nanowire, right? And in order to confine, so what gives localization length is determined by the gap which you induce. Superconducting gap is usually smallest comparison with Zeeman gap. And then it means that you try to induce proximity as strong as possible in these nanowires, at which Majorana are well localized in one end and other end and do not see each other even in a relatively finite few micrometers nanowires. And this was a development. If you want to induce a strong superconductivity, what we would do, we would take a nanowire, how it's shown in the cross section, and we will introduce superconductivity, let's say by epitaxial growth, such that the contact between semiconductor and semiconductor is strong. And for superconductors, as usually we use aluminum. Because in this case, first we expect that we will get very strong superconductivity. Now our expectation that this would be very good interface with our disorder, and we will see hard gap. So hard gap means that you should have no states in superconducting gap. So it should go to 0. So here you see that still you see finite density of states even in the middle of a gap, even without Majoranas, but for majority of experiments, sometimes this curve is even more smooth, which tells us there's some imperfections. So we have some states at 0 bias, even at finite, relatively low temperatures. So this is a motivation to have strong coupling between the shell, superconducting shell, and semiconductor. But of course, as quite often in physics, from this we don't only have advantages, but there's also disadvantages, about which I would like also to talk a little bit. So what we are coupling here is we have a superconducting system, let's aluminum, which has very large Fermi energy, and we couple it to the semiconductor, such, let's say, indium arsenide, where Fermi energy is supposed to be tuned close to spin orbit, so it's scale maybe of 1 milli-electron volt, and we bring these two systems close to each other in strong coupling regime. So what we can achieve here is that, of course, the first effect we can introduce in terms of, let's say, green function. We can introduce parameter gamma, which would describe how well this coupling works. So it means that if gamma is equal to 0, it corresponds that the entire time which electron has, it sits in nanowire and never goes to the superconducting shell, right? So it corresponds to absence of coupling. And gamma even 1, it would be opposite regime, when electron spends more time in a superconductor than in a wire, so fully absorbed by superconductor. Or you can reformulate it if you would diagonalize this matrix, let's say in time-binding model numerically. You can plot wave function and to see how much support wave function has inside of nanowire and how much it has support inside of semiconductor. Which was naturally tells, let's say, that if majority of the support of gamma is equal to 0, so you spend all time in a superconductor, then we would find that this proximity-induced superconductivity is the best, right? Because you live in superconductor and you see full gap delta. So this is a fact which we would like to have. You would have a proximity gap which is as strong as in a bulk superconductor, and you cannot be in a better situation. But of course, the drawback which you would play if your gamma is equal to 1 or 0, so you spend all your time in a superconductor, and it means that you don't see any semiconducting properties. You don't pick up that you have a large G factor or that you have a strong spin orbit. So all these parameters and effective green functions, they will get renormalized. So it means, let's say in the case of a G factor, it's most probably easier to follow, because you can say if you have a semiconductor with G factor 50, you have a superconductor, usually G factor 2, and your wave function, let's say 80% of time spent in superconductor, then you expect that all properties that you measure G factor will be more as a superconductor and not as a semiconductor, because support there is very small. So this results that we have a kind of interplay between two effects. So you want to have a large gamma, so gamma close to 0 to have strong superconductivity, but at the same time you want to have also semiconducting properties, which requires gamma being more close to 1. And by tuning these parameters, so how strongly one couples two systems, we can go from one regime more semiconducting behavior or more superconducting behavior. Another effect which renormalizes gamma is not only parameters at spin orbit or G factor or mass, but also chemical potential. As we know from a quantum dots, let's say when you couple two levels as shown here, and they're in resonance, then you would have a shift of chemical potential. They would repulse each other, which usually results also of shift of a chemical potential in a semiconductor. So all these kind of effects of strong coupling one can summarize. So So here, this is a numerical calculation, but we also reproduced all this curve analytically. In green function approach, here parameter T tells us how strongly we couple. So T equals 0, it means there's no coupling between superconductor and semiconductor. In this case, proximity gap is equal to 0. And then we start to increase with T, and we see that the proximity as expected gets better and better. So the stronger you couple, the more proximity you get. But at the same time, you also have effect on the mass. So mass starts to go more to metallic case. And what is the most disappointing for Majorana is that spin orbit energy and G factor also going down. So even take nanowire with G factor 15, but strongly coupled to a superconductor, when you start to go back, let's say, to G factor direction, more close to 2. And as I said before, there's also effect of metallization. So it means if at finite T equals 0, no coupling, we have, let's say here, 4 subbands, which are relatively spaced from each other. Now we start to strongly couple, the system starts to get more metallic, so mass changes, so the spacing between bands goes down, which effectively also results in the shift of a chemical potential. So it means, let's say, if we tune initially our chemical potential close to spin orbit crossing point without shell, and then afterwards you put the shell, everything would be detuned, you would have more bands occupied due to the effect of metallization. So let me summarize the effects. So what happens? So again, in this plot, I show the picture, let's say, nanowire without any shell. So here you see a splitting between bands and several bands occupied. So here you can still see effect of spin-orbit interaction with this hand. But at the same time, if now I introduce shell with relatively strong coupling, so introduce very good proximity, you would see that bands would go down, so I shift chemical potential in nanowire, and I would also renormalize spin-orbit interaction such that it gets much smaller. And small spin-orbit interaction is very harmful for getting Majorana fermions, because the smaller spin-orbit interaction is, the more difficult to get into topological phase such that you have a localized Majorana fermions. So usually when one chooses material for experiments, one wants to have ones with very strong spin orbit. So at the end, you can say, okay, this metallization effect plays also harmful effect due to the renormalization of a G factor, because in order to achieve topological phase, we need to go to the regime that Zeeman, let's say, dominates over proximity-induced gap and also compensates the shift of a chemical potential away from spin orbit energy. And if we also assume that we have little control over the position of a chemical potential due to the strong coupling to superconducting shell, when it gets difficult to be in topological phase, let's say for orbitary nanowire, most probably one needs to try to measure several, most probably hundreds of nanowires, and one of them, the chemical potential would be in optimal position, such that we can say, okay, with delta mu is equal to 0, we don't need to compensate, we compensate only for proximity-induced gap. And then we can achieve a topological phase, let's say, for fields around 1 Tesla. If we are not lucky and this shift of chemical potential is so strong that we're away from any spin orbit crossing point, then, let's say, it would be difficult to achieve topological phase, because magnetic fields needed to compensate shift of a chemical potential would be in 100 Teslas, and it would be not achievable. So here, one kind of pays the price for strong proximity. So the conclusion from this that maybe one should not try to induce very strong proximity. There should be some interplay that you still have enough delta, but you did not fully suppress the G factor inside. And then with few attempts of positioning chemical potential, one can still achieve the topological phase, but one should have some luck in this task. The question, of course, still there's many experiments in which one sees stable zero bias peaks. And that's why last 2 years there were a lot of field activities trying to understand, can we actually, are Majorana fermions are the only states which can pin to 0, or can we, let's say, do it also with Andreev bound states? So there would be more complicated effects. And the setup which I want to consider now is the following, because I want to have Andreev bound states, I need to have normal sections, so section without superconductivity. And this is what's shown schematically here. So I assume I have a nanowire. It's end of nanowire is a normal state, so it's not covered by superconductor. And I also assume that in the superconductor, I have the shift of a chemical potential such that I'm so far away from spin orbit point, but even with a large magnetic field, I do not enter here into the topological phase. So it means I exclude that there could be Majorana fermions, and I study the spectrum of Andreev bound state. And here in this modeling, we assume that, let's say, that also spin orbit interaction and Zeeman energy has a jump in the superconducting parts. Let's say the G factor in normal part is larger than outer, but at the end it happened from it's simpler for us to solve it analytically, but in numerics we can check both regime, and it happened to be not important. Only what is important that there's a normal part, so delta should be equal to 0 here, and that the chemical potential is shifted under the superconductor such that there's a Fermi velocity mismatch between normal part and one which is approximatized. So in general, to find the spectrum of Andreev bound states in this problem is difficult, but in theory we can assume that we have a regime when energy is close to 0, when we can expand, and we can find the equation under which conditions with energy equal to 0 could be found. And then here we require that the cosine of 2KSOL is equal to 0. So it's kind of Fabry-Perot condition of resonance. And in this case, if we satisfy this condition, then we would find that energy is exponentially close to 0. And this is a curse which found by time-binding localization, so it's numerical solutions indeed. We can look how the spectrum of lowest Andreev bound states changes as function of KSOL. So either we can play with a shape of the dot by gates, or we can tune spin orbit interaction of Rashba time. It's very well possible to tune it with electric field. And then indeed we will see that there's such periodicity. And let's say if you're in the point where this cosine goes to 0, we find that Andreev bound states for some value of Zeeman field, it pins to 0 and stays at 0. Right, and let's say this picture very much reminds one which you would see usually for Majorana fermions when it goes to 0 and sticks to 0 for some range of magnetic fields. If we deviate, let's say, from point B, go away from resonance, let's say in the point C, then we'll see such a double picture. So it's double I. So now you can imagine that, let's say, if you do transport measurements, you also have each of these lines would be broadened both by temperature and by coupling to the lead. So that here most probably you would see just one much thicker zero bias peak. And of course, if you go opposite to the resonance, you go to the point D, then you would see that, okay, now there's no pinning, right? So you're really far away from zero energy. This is the behavior which you would expect for Andreev bound states. And the conclusion from this, yes, like some Andreev bound states can mimic the property of Majorana fermions. Recently, I could recommend we have written a review considering different mechanisms how such pinning could occur in Nanowire with Rashba spin orbit interactions. There's additional scenarios, let's say, when your potential is smooth, so can transition from superconducting to home plot smooth. You also can get so-called quasi-Majorana bound states, which again would pin to zero energy for some range of magnetic fields. And the outcome, of course, of such now we can see zero bias peak in experiments. It's not clear if it's Majorana or not. It could also be Andreev bound states. And such picture similar to what we have predicted for Andreev bound states, let's say we observed also in this paper, in science paper by Deng, first offer, in which you can say, okay, this looks very much what we expect for our Andreev bound states, that if you tune the gates, it means you tune either spin orbit to size of the dot, when you can go through such blobs. So there's some area where you stay close to zero, which corresponds to our area being here, close to the resonance. And now if you tune to this point, choose the point in the gate when you're at zero, and afterwards you increase magnetic field, you can expect that there will be some pinning, which would reproduce some features of Majorana fermions and give you positive false for observation. Of course, you can say it would be good, let's say, if you go for quantum computing and really want to see Majoranas to observe, kind of exclude such Andreev bound states, which in this case, you can say it's relatively easy because if you would not have a dot, right? So if you would not have this normal section, between superconductor and valid, when most probably you would not have any Andreev bound states, and then you can distinguish. But in many experiments, what we see is that the zero bias peak emerges from some Andreev bound states. So it means that even at small magnetic field away from topological phase, we can see that there's some bound states inside the bulk superconducting gap. So it means there's a presence of section, of normal section, which potentially could host also false Majoranas, so-called Andreev bound states or quasi-Majoranas. And if we can get rid of an experiment from a dot, which could be possible in some setups, then we can avoid such confusion with Andreev bound states. Another comment which I would like also to make here, that with pinning of Andreev bound states to zero, in principle, one can observe it also experimentally at finite energy. So it's a general feature that if we have a normal section coupled to superconduct, in this normal section we have very strong spin-orbit interaction. So it means that you have a spin which rotates many times in the size of a dot. And then you apply magnetic field perpendicular to the direction of spin orbit, that on average, this rotation caused by spin orbit averages out the effect of magnetic field, and your G factor basically gets exponentially normalized by spin orbit strength to the length of the dot. And this is one, we can saw it with our collaborators in the group of Schonenberg and Basel. We also saw that you can find such states which have a finite energy, and also pin, they're not sensitive to magnetic field up to fields in which you kill superconductivity due to the presence of strong spin-orbit interaction on the dot. So at the end, you can say nowadays it's not anymore peculiar for Andreev not to be sensitive to magnetic field. You can find it's a more feature of having strong spin-orbit in nanowire when you can get this insensitivity. So another comment which I would like to make, so before I have focus on nanowires, and here I should comment that such scenario of Andreev bound state being pinned to zero is also possible in two-dimensional superconducting system. So the setup is there is usually that you have a Rashba 2 deck coupled to a superconductor, which is again assume, let's say, S wave, and you have a vortex. So let's say it could be some normal section or just a parameter where delta goes to zero. And for this vortex, you can usually assume that you have a odd flux, such that you can enter a topological case again if Zeeman field in the normal section dominates over superconductivity. And in this setup, similarly, we could study, let's say, even vortex. So it means either there's no flux through it, so it's only Zeeman field, or there's even flux through. And this similar, we can see that there's a point if you tune size of a dot and spin orbit in some point, when you would see that at finite Zeeman field, you can get a pinning close to zero, similar to Majoranas. And in this case, we know that it's even vortex, so we cannot be, this state is not a Majorana fermion. Or similar, we can consider the case when we have odd vortex. So let's say one vortex going through, one flux goes through. And then we can be potentially in the topological phase, which is demonstrated, let's say, in this numerical calculation. So in point C here, we see the signature of a bulk gap closing, and we enter the topological phase. But at the same time, we see that the pinning occurs also before this phase. So it's point B. And this is bound states, Andreev bound states in the vortex. And this we can see in the wave functions. Let's say if for Majorana fermion in topological phase C, we see that we have a Majorana fermion, one Majorana at the vortex, and one Majorana which is outside. So they have a different support. And we can check that indeed the self-conjugated operators, it's real Majoranas. So what we see in B, that it's also zero energy bound state, but it sits only, it has support, both electron and hole part have support only close to the vortex. And similar how done it was in nanowires, here we can also recompose it in some symmetric antisymmetric combination and see, okay, symmetric antisymmetric combination, they have slightly shifted support, so you can represent it in terms of two quasi Majorana bound states, but they strongly overlap. So to use them for quantum computing could be maybe very challenging because a disorder would also couple them. But the outcome here, yes, so also in two-dimensional systems, there could be Andreev bound states in the vortex pinned to zero for some range of magnetic field. and not sensitive, let's say in this case of odd vortex, we are also not sensitive, there's no fine tuning in spin-orbit interaction on length of a dot. So this is, again, due to renormalization of G factor, we arrive at it's close to 0, and then we just spin, and doesn't matter if it was Majorana or not. And now I would like to move to the next topic of my talk. It's higher order topological phases. And in this case, what is the difference here? It's kind of next step in complexity from a nanowires. So here we consider either 3D or 2D systems. And let's say if you consider 3D system, then we consider so what would be topological insulator in standard sense? You would have everywhere on the surface the helical states. And here we can consider so-called second order topological insulator with host hinge modes. So it means if you have a cube, there's a helical or chiral modes which runs around of hinges. Half of the hinges have this mode. Or if you go even further, you can imagine, let's say in 2D system, you have a 2D system and you have a bound state here and bound state here. So what is important here is to also emphasize that Hamiltonian, so system should be uniform. So it's not like, let's say, that you have some H modes running around, and when you make superconductor and superconductor and magnetic field domain involved and localized. So here the Hamiltonian is assumed to be uniform. An example of such system, let's say for 3D topological insulator high order, it was argued that, let's say, bismuth could be represented as a type of such system which host hinge states, helical modes which run along the hinges and not having any surface states. And some first experiments were done in this direction. So now in my group we have worked in the question, can we actually also get topological superconductors of higher order, let's say, or second order? And in this case, we have considered the setup in which we take a bismuth. So we already know that it has hinge modes, and we proximatize it with a bulk superconductor. Let's say you can cover it when the entire surface of bismuth becomes a superconducting. And we assume that, of course, that the bulk gap of bismuth is larger than the proximity which we induce. In this case, we can focus only on hinge modes and to consider how they're getting gapped out by a superconductor. And in this case, we consider, so we have a different hinge mode, and proximity, we can consider different regimes. So one of them, how the proximity works, as we discussed before, you take a Cooper pair from a bulk superconductor, and then the entire Cooper pair tunnels in hinge state. Right? And then you introduce pairing correlation inside. And there could be different processes. So one of them is local. So you have a Cooper pair, and then both electrons tunnel in one of these hinges. They go here. Or you can consider non-local processes, so-called cross-Andreev, when you take a Cooper pair and you separate it. That means one electron goes, let's say, on one hinge here, and another electron goes to another hinge. And this process is called cross-Andreev. So it was observed experimentally in quantum dots. And why it's usually in order for cross-Andreev to be dominant, you need to have strong electron-electron interaction, such that when you put two electrons close to each other, you pay a price due to electron-electron repulsive interaction. And then that's why you would prefer to separate them. So similar as in previous setups, now we have two ways to open the gaps. Let's say if you would consider the spectrum of two hinges, right? They have the same chirality, have everywhere the same chemical potential. So either you have a local pairing, and then you couple electrons to each other with superconductivity from the same hinge, or you have this cross-Andreev, and it means one electron goes, let's say, here, the first hinge, another one goes here in the second hinge. And this is two ways to open the gap. They compete with each other. And the topological phase occurs if this cross-Andreev way, so when you prefer to separate, dominates over local pairing. In this case, one can generate Kramers pairs. So it means that the ends of these hinges, we have a Kramers pairs of Majorana fermions. And as emphasized before, such phase could be achieved only if you have strong electron-electron interaction. So using RG calculations, one can predict, and this green area kind of shows the stronger the local pairing dominates in non-interacting regime of a cross-Andreev pairing with strong interactions, I would need to have to go to the topological phase. Right, so this was about generating Kramers pairs, but let's say this experiment with coupling superconductor, maybe it could be challenging to do it again if there's always a danger that we shift away the Dirac point in the spectrum. So that's why we also have worked on how to generate, let's say, such Majorana fermions in two-dimensional system, corner state. So here the idea would be to find a ways to generate, let's say that we have two-dimensional system. It's composed of the following structure. We have two Rashba electron, two decks. So it means they have strong spin-orbit interactions. They couple weakly to each other due to the barrier. And in each of them, we induce proximity from two superconductors. And for our setups, to let's say if you want to begin to keep time reversal symmetry, we assume that the phase between superconductors either absent or is zero, which could be tuned by flux, or we can also put set of magnetic impurities and then can generate pi phase shift. So what means that we have Rashba 2 deck? So the spectrum looks like as a parabola in 1D, which I have shown before, but just rotating around this axis. So it looks in this way, right? And you have two such parabolas. They have the same opposite direction of chirality, so how spin rotates. And now we can couple them. And again, as you can see, if I, let's say, assume my chemical potential is close to the spin orbit crossing points, there's two ways how I can open a gap. So either I have a superconductivity, when it's standards is everywhere gap opened by superconductivity. Or I can consider that now I have two such parabolas, an upper layer and lower layer, and there's a tunneling between them, right? And similar to what before magnetic field doing, with tunneling is effective around point k equals 0. And in this point, by tunneling, you would open the gap, right? Because you couple right and left movement, so you open the gap there. So it means that k equals 0, we have two ways to open the gap. It's either by superconductivity or by tunneling. And again, as you can assume, if you would solve it, I think everyone can guess now that if tunneling is dominates when you have at k equals 0 gap opened by tunneling, outside you have a gap opened by superconductor. It's again this effective domain wall which we have. And it means the system should be in topological phase. In our case, so far we did not apply magnetic field, so the H modes which we have, they're helical. So this could be found also by solving the spectrum. So you have a mode, let's say around 2D setup, it runs around, and there's actually two contra-propagating modes, which are Kramers partners of each other, superconducting. So you can call them helical topological superconductors. They also have a character of Majorana fermions. So this phase is the first order topological phase. Now I'm trying to open a gap there in this spectrum to get bound states. So how can I do it? I can, of course, the first thing to apply magnetic field, it breaks time reversal symmetry and should gap out edges. But what is interesting is how exactly this gapping out works. So the gap which we open by magnetic field is at this point, let's say at kx equals 0. And then I want to know what is the polarization of these states, right? And if my kx is equal to 0, when I look at this Hamiltonian, kx goes 0. So now I have sigma 2 Pauli matrix is not entering anymore into the Hamiltonian. So it means my states at k equals 0 eigenstates of Pauli matrix sigma 1, right? So it means an H which propagates here, kx equals 0. It goes along the H. When I have either one state, so sigma 1 is equal plus 1, another minus 1. And then you can also see that due to inversion symmetry, you can make argument that in opposite edge, where you change the direction of propagation, when spin would flip. The same argument is also true for y direction. So it means when these H states go around, and actually the spin projection is rotates around, which kind of typical for what you would expect for a Rashba system. And now I apply magnetic field, I try to open a gap, and what is important for us is the sign of a gap. So it's not surprising that I have a gap. The question is, do I get a domain wall if I have such in-plane magnetization? And indeed, in this case, one can show, but now, let's say I try to gap out upper edge and lower edge. And the size of a gap, because polarization of right and left moving modes opposite, when the projection of magnetic field perpendicular component also opposite, right? And in this case, I would find out that I have a size of a gap which is upper edge and lower edge is actually, they have the same size, but they're opposite to each other. So it means, and in these vertical edges, it's again opposite. So it means that in this case, I need to generate some domain wall, because I know that vertical has opposite signs and horizontal sides, they have opposite signs. So there should be some domain wall where a gap changes the sign, and the point in which it happens is actually given by projection of magnetic fields. In this case, it would be at this corner. So what it means that now if we diagonalize, let's say in time-binding numerics, so I would find that there's a red gap, here's a blue gap, and there's a corner state in which I could find the Majorana corner state. So it would be single, there's no particle, no time reversal degenerate, so I have one Majorana here and one Majorana here for given direction of magnetic field. So now if I would start to rotate magnetic field at some point where field is parallel to the edge, and in this case, I cannot open a gap, right? Because if I apply magnetic field parallel to polarization, there's no gap opening. And then the system stays gapless. And now if I continue to rotate magnetic field, then at some point it would switches on and will be given in opposite corners. I can also consider the configuration and I have a hole in the middle of the system. In this case, I would have states at 4 corners, so it would be 4 Majorana fermions. One should also notice that in this setup, because I said I have 2 superconductors, I can also break effectively particle time reversal symmetry by making a Josephson junction, so there's a phase between first and second superconductor. In this case, there's a gap opened by phase difference in Josephson junction, which would sum up with a gap which I have by Zeeman field. And there could be such competition that now I don't have gap anymore in 2 opposite corners, but I could also shift it to adjusting corners if there's a phase difference between 2 superconductors. And now one can ask, so this is kind of interesting structure, can I see this polarization of a gap also in experiments? So let's say if I try to probe topological phase, I don't only want to see that I have a corner states which are 0 energy, I want to see some signature of a topological phase transition. And this is what we recently did. Also, we simulated, let's say, STM experiment when you come with spin polarized tip, in this case, perpendicular to magnetic field, and you try to see the current, how it goes through the tip. And what we found when in topological phase, when we don't have any Majorana fermions, which we can achieve, let's say, by detuning from let's say if you destroy H states when you apply magnetic fields, there's nothing happens, the system is in trivial phase. In this case, we don't have any interesting structure on spin polarization at the edges. And in the topological phase, when we find that there's such quadrupole structure in spin polarization. So it means that if you measure, let's say in the middle, you usually don't have any signal because the gap there is opened by a superconductor. But if you come here, so effectively time reversal symmetry is preserved there, so there's no signal. But if you come to the edge and you look at this gap, which we have opened by applying magnetic field, when you see the texture, let's say that indeed in one case you have positive current. So if let's say it's spin polarized up, here it's polarized, spin polarized down, up, down. So we can kind of mimic, reproduce the texture. The only kind of disappointment in this texture, we do not see that Majorana sits at these 2 corners and not at this one. And we have here also consider setups not only with 2 Majoranas, there's also proposals when you have 4 Majoranas, so you have a corner state at each corner. But this quadrupole structure in spin polarization stays the same. So we have concluded that most probably it's a general feature of this high order second order topological superconductors 2D that these corner states, presence of corner states in the spectrum is also accompanying by changing of structure of bulk states of H modes, and they have such quadrupole polarization, which signatures of a domain walls at corners. What should I also, in our group, in collaboration here with Professor Daniel Watts and with Alexander and Sebastian Tamoki, we have also actually shown that this corner state high order topology could be taken also not only in electronic systems, but also you can see can construct magnon insulators, so magnetic systems in which you can get hinge modes, let's say, of magnons or corner states of magnons. So it's not only for electrons relevant such confinements, but also for magnonic systems. And in the rest of my talk, I would also should mention that we went one step further from Majorana fermions to more exotic states as a parafermion. So what is a parafermion? It's a state which, let's say for Majorana, gamma squared is equal to 1, so operator gamma is equal to gamma dagger, but you can generalize it to more general for case when gamma to a power n is equal to 1, and let's say the most interesting case is n either 3 or 6 or 4. This is what is discussed in the literature, and it has more interesting for promise of having more exotic braiding statistics. You can perform more operations in topologically protected case. And that's why kind of Majorana fermions interesting, except of fundamental physics, also for promise of more universal topological quantum computing. So how one can construct a corner state? So we looked recently at if it's possible to get parafermion corner states, we end up with several setups. The problem here is that we want to discuss two-dimensional system and with strong electron-electron interaction, which allows us to do it only if we work in a strongly isotropic regime. So we should have some one-dimensional channels constructed either out of nanowires or constructed via coupling some channels, let's say in bilayer graphene, when you twist it, when you have effectively 1G channels, and you can consider proximity. And then you can consider different types of couplings. So standard ingredients, again, we have superconductivity, we have strong spin-orbit interaction, and we choose particular type of coupling terms between 1D channels. Let's say in one of setups which we consider is again is similar, but we have two nanowires coupled to each other with opposite direction of spin-orbit interaction. And we introduce again that we have delta, proximity-induced superconductivity, so we have delta, and you now allow tunneling between these 2 points gamma. And in this case, again, at k equals 0, you have a competition between gamma and delta. And what is interesting in this setup, instead of saying, okay, if my gamma dominates over delta, I'm in topological phase and I have a localized Majoranas at the end. But it would not bring us further, because in this case, we want to have a Majorana channels. So it means that we tune close to the point that gamma is equal to delta. So it means you arrive to this critical point where two mechanisms compensate each other. And in this case, we will find out that in these two coupled double nanowires, we have Majorana fermions which live. So we get the channels of Majorana fermions in each wire, or in combination of these coupled wires. Now, if we couple these Majorana modes to each other in such a way that similar, let's say, to SSH model, you gap out everything in the middle, and you end up with only Majorana fermions, chiral Majorana fermions at the edges. And so it works like first we go to the critical point, such that Majoranas, which we have two Majorana modes propagating inside the wire, and then we find a specific type of a coupling, which in our case we have again interplay between cross Andreev and tunneling, such we can gap out by this coupling all Majoranas inside, and we left out only with Majorana outside and on one edge and another edge. And then by topological continuation, we can say, okay, if you have mode which goes here, mode which goes here, this mode is chiral, then it should turn, and it could also go in our two edges. It means that in this sector, we found the chiral mode which runs around. But now reminding that our system is actually time reversal invariant, it's also, we have a partner mode, time reversal partner of it also runs in the sample. So this way we can construct a helical fractional topological superconductor. So in this case, let's say we would have modes which would run around here in the setup. And similar, so here I did it with Majorana fermions, but one can also think how to generalize it to fractional regime. And here maybe I would go more in details. So before I had a chemical potential tuned to spin orbit energy. And now I tune it down, right? And now I can say, okay, now if I want to introduce some gap by tunneling, I cannot go directly, right? Because if I would tunnel from this point to this point, when I go from positive momentum to negative momentum, so obviously momentum is not conserved, and I should not, this tunneling should be suppressed. But I can compensate for this if I would consider backscattering events. So it means one electron goes from here to here, and then in each wire, I also backscatter one electron here and one electron here. In this case, I have a term which requires strong electron-electron interaction, because electrons should know that there was some tunneling. And in this case, momentum is conserved, spin is also conserved. And this allows me to rewrite this system in terms of a parafermion. So I would repeat the same structure, however, with more exotic particles than Majoranas, but they're now parafermions due to the kind of description which you use here with strongly interacting terms. And instead of competition between these two terms is now given by self-dual sine-Gordon model. So I have tunneling term, I have superconducting term. I need to bring them in competition to get a parafermion mode propagating. And going again, similar to lines for Majorana fermions, I can introduce parafermion fields. They would also run around, just with more exotic statistics. And now again, if I would apply magnetic field, I would open a gap at all edges by breaking time reversal symmetry. If field has projection on all edges, I open the gap, and again there would be corner states which was sitting. But in this case, due to non-trivial nature of my helical modes already, I would the states which I would localize would be parafermions and not, let's say, Majorana fermions if I'm in this fractional regime. So it means I would get, let's say, one parafermion here and one parafermion here with more exotic statistics. And similar again here, if I would start to rotate magnetic field, I can bring them from one corner to another corner. To give an idea, in principle, there's additional ways how you can consider, right? So here I was coupling nanowires, but as we saw, like, let's say, in terms of interaction, it was very difficult to describe it, right? I needed to work on this large energy liquid. And that's why later was also approach of coupled layers was developed. It works very well for non-interacting cases, because similar as described before, I would have this Rashba nanowires. Now the spectrum of each layer is given by Rashba, right? You can say, looks like 1D system. I just need to assume that I take the spectrum and rotate around, and I explore this rotation symmetry. And similar, by introducing different types of tunnelings, I can find the ways, let's say, if I have tunnelings here, so it's not superconducting system, there's only tunneling between layers. And I can say, first I have very strong tunneling T1, so between here and here. When it opens a gap, so these 2 points gets gap out. Now introduce also strong T2, it gaps out these points, right? This point is already gapped out by T1, and we can continue it from layer to layer. And what you would notice that there's a partners here and here which do not have any tunneling partners. They did not interact with anyone, and then they stay gapless. So you say, okay, this mode stays gapless, and this mode stays gapless. And now if I apply the properties of that I have a system which is rotationally invariant, it means that in reality I have a Dirac cone on the surface. And this Dirac cone is also helical because it comes from helical structure of initial Rashba layer. And in this case, I can easily show that, okay, in this case, I have 3D-dimensional topological superconductor with helical Dirac cone on the top and in the bottom, which rotates. And this is idea how we kind of this coupled wire approach could be also generalized to couple layers when you consider coupled layers of two-dimensional systems, right? And here we can also try to make arguments to say, okay, if you have strong electron-electron interaction, let's look if you can apply similar types with backscattering when you say, oh, if you tunnel from one layer to another layer, you do not conserve momentum, so you try to compensate by electron-electron interaction. And then you choose the terms which help you to particular feeling to satisfy. And then you can apply argument with strong interactions. When you open a gap, these processes are very favorable. So that's why you would open a gap and you would go to fractional topological case. I know that my time is runs out, and so maybe advertise a little bit that you can continue this game. Also the case when you do not open a gap, but you can find still resonances between different Fermi surfaces. In this case, there's no Rashba, they're just split by Zeeman energy. So if you can find Fermi surfaces, let's say, satisfy some momentum conservation, K1, K2, K3, let's say in sum is equal to momentum K4. So it means you can have electron backscattering processes which conserve momentum and couple different surfaces when with very, very heavy formalism, which only our postdoc Dima Miserev can go through with green function, we can show that you also get special properties. You would find that you can even get something similar to SYK model without any assumptions of random interactions. It just pops out with green functions are described by similar equations. And this brings to end of my talk. So to conclude, I have considered Majorana fermions come a little bit interplay between theory and experiment, and reviewed why sometimes it's difficult to distinguish Andreev bound states from Majorana fermions. I have talked about second order topological insulators and superconductors, so when we can have Condensed states with special focus, that actually it's possible also to construct fractional fillings. And a little bit I mentioned how it works. And at the end, I would like to thank my group with whom I have done work. So it's also a collaboration with a group of Professor Daniel was. So this fractional parafermions was done mostly by Katarina. So Yannick has done work on this second order topological states generated by magnetic field recently with Kirill and Manisha, Flavio and Alexander and Sebastian. I mentioned there also was work on higher order Magnon stuff, and this was done by these two gentlemen. So I would like to thank all my collaborators. Thank you.